again in the last session of today. So what I will do, I will be covering one basic numerical, right? And if we perform that solution, we will able to have the calculations learned what Professor Dr. S.K. Srivastava has elaborated till now. Because he has taken some basics, then arrived at some conclusion. So all those things needs certain calculation, certain stoichiometrical procedure we have to go through and make the calculation. So by solving this problem, we will able to understand each and everything, and we'll able to calculate such kind of calculations, right? Yes. So the problem statement is nitric acid is produced in the Ostwald process by the oxidation of ammonia with air. That is what we already know. In the first step of the process, ammonia and air are mixed together and passed over a catalyst at a temperature of 700 degrees centigrade. Right? The following reaction takes place. 4 moles of ammonia reacts with 5 moles of oxygen, and we get 6 moles of water and 4 moles of NO. This is the reaction which takes place over the catalyst, right? The gases from this process are passed into towers where they are cooled, and oxidation is completed according to the following theoretical reactions, right? 2NO, okay, which we received from these earlier reactions. 2NO plus O2 gives 2NO2, right? And then this NO2 gets reacted with water, that is 3NO2 plus 2 plus H2O gives us 2HNO3 plus NO, right? And this kind of reactions gives us the nitric acid, right? The NO liberated in the final step, right? The NO liberated in the part reoxidized and forms more nitric acid in successive repetitions of the above reactions. Mouse मेरे पास में आ सकता है? Can I get mouse? Okay. The ammonia and air enters the process at a temperature of 20 degrees centigrade and pressure of 750 mmHg, right? So this is what the conditions of the inlet ammonia and air enters. The air is present in such proportion that the oxygen will be 20% in excess of that theoretically required for complete oxidation of ammonia to nitric acid and water, right? So this is certain statements of the gist of problem is given, right? The gases leave the catalyzer at a pressure of at a pressure of 743 mmHg and a temperature of 700 degrees centigrade, right? So what we have to calculate is part A, calculate the volume of air to be used per 100 cubic feet of ammonia entering the process, right? So as I told you, air and ammonia enters in the process. So suppose the ammonia is entering and the volume of that is 100 cubic feet, right? What will be the volume of air to be used? So that is to be calculated. Then part B, calculate the percentage composition by volume of the gases entering the catalyzer, right? So at various stages the process will be. So to the catalyzer, what composition of gases will be entering, so that we need to calculate. And part C, calculate the percentage composition by volume of the gases leaving the catalyzer. Okay, so leaving gases also composition we have to calculate, assuming that the degree of completion of the reaction is 85% and that no other decomposition takes place, right? So this is another statement here it is given. Then part D, calculate the volume of the gases leaving the catalyzer per 100 cubic feet of ammonia entering the process. and in last part, that is in part E, we have to calculate the weight of nitric acid produced per 100 cubic feet of ammonia entering, assuming that 90% of the nitric acid entering the tower is oxidized to nitric acid, right? So as we all know, during the solution of any stoichiometrical problem, we need to define the basis, right? Either 1 gram mole or 1 lb mole, right? Or 100 cubic feet of volume, right? So we need to decide one particular basis, and based on that we have to proceed the solution, right? So here we can take basis as 1 lb mole of ammonia, right? However, it is said that in maximum calculations they have been asked find out certain things if there is 100 cubic feet of ammonia entering in the process, right? So rather than taking the volumetric basis, it is always good to use the lb mole or gram mole as basis, right? So what we will do, we will be assuming 1 lb mole of ammonia entering in the process, right? And then we will find its volume, and accordingly we will be converting the desired answers then, right? If that much of volume is being entering of ammonia, right? If enters 100 cubic feet of volume, then how much will be the compositions and all those things. In that way we will do, right? So now the reactions, the overall reaction is something like this. We have seen the 2 or 3 reactions. If you combine all those, right, we will be landing up with this this first reaction, that is 4 NH3 plus 5O2 gives 6 H2O plus 4 NO. Then 2 NO plus O2 gives 2 NO2, 3 NO2 plus H2O gives 2 HNO3 plus NO, right? So if you do combine all these reactions, it will be landing up with this resultant reactions, right? So NH3 plus 2O2 gives HNO3 plus H2O, right? Now theoretically we can calculate how much oxygen will be required, right? As we decided that our basis is 1 lb mole, by looking at the reactions you can easily tell that 2 lb mole of oxygen is required, right? If we would have taken basis 100 cubic feet of ammonia entering, it would have been difficult for us to get known how much oxygen will be required, right? Because volumetric kind of calculations is not being reflected by virtue of looking at the reaction. But the beauty of our assumption is, okay, by looking at the reaction itself, you can tell that 2 lb mole of oxygen is required theoretically if the 100% conversion of the reaction is, right? Yes, so here oxygen required will be 2 lb mole. Now how much oxygen we need to supply, right? It is stated in the problem statement that 20% we have to give extra, 20% excess, right? So 1.2 you have to multiply, and that much of oxygen we need to supply, right? So 2 lb mole multiplied by 1.2, that is 2.4 lb mole of oxygen we have to supply, right? Again, oxygen generally is not available in the pure form. So wherever oxygen is required in industry, we supply air, right? However, sir told that if you supply the entire air instead of oxygen, okay, so many things, okay, this nitrogen will take away along with that, heat and all other kind of thing, okay, the exhaust gases will be more, right? So we need to handle all those, okay. But for the sake of economical point of view, right, rather than separating oxygen from air and using that, okay, what we do, we supply the air, right? So how much air will be supplied? 2.4 divided by 0.21, okay, because stoichiometrically we assume that air contains 21% of oxygen and remaining 17% of nitrogen, okay. We neglect all other gases. right? So the air to be supplied will be 2.4 divided by 0.2, right? So in that way 11.42 lb mole of air we have to supply, right, as per the resultant reactions we could conclude, right? Yes. So now you can find out volume of this much of air, right? If we have to supply 11.42 lb mole of air, how much volume of air we will be supplying? Because you know, the moment we decide that this much of lb mole of air we have to supply, right, we will not calculating the lb mole available in the some climate, and then we will be using exactly that. Okay, what we will be doing, we will be using certain volumetric device, okay, which will be sucking the air and will sending that into that particular process, right? So depending upon the condition of available air, I mean temperature and pressure, right, we will be taking the volume, right, how much volume or how much volumetric flow rate of the air we have to use. So that again we have to calculate, right, because we need 11.42 lb mole of air, right? If we give more supply, again that issue will be there, that it will be taking away the your heat or your some reactants also, some byproducts will be formed unnecessarily more. So again its separation and all that kind of problem you have to face at the end, right? So it is better to have very precise excess percentage, okay, and very precisely measured supply of either feedstock or the air, right? Yes. So now this 11.42 lb mole of air needs to be converted into volume, right? So at what temperature, at what pressure it is available, you get it identified, okay, and then converts its volume, right? Volume of 11.42 lb mole of air to be supplied, right? So we know the ideal gas law, right, and that you can use, okay, P1 V1 upon N1 T1 equals to P2 V2 upon N2 T2, right? So we know N1, we know N2, okay. Suppose at left hand side, okay, N1 means 1 lb mole of any gas, either air or oxygen or nitrogen, right, occupies how much volume at what temperature and pressure, that we know on left hand side, right? So here you see at 0 degree centigrade temperature, right, means 273 Kelvin temperature, okay, and 760 mmHg of pressure, any gas, okay, any gas, if it is 1 lb mole, will occupy 359 cubic feet of volume, right? I have written the temperature in Kelvin and pressure in mmHg, right? However, you can convert it into psi, right, in Rankine, and accordingly you can have the calculations here directly on, because on both sides if I use the same unit, no problem, right? Yes. So at 273 Kelvin temperature and 760 mmHg pressure, 1 lb mole of air will occupy 359 cubic feet of volume, that we know, right? If again 1 lb mole of air available at 293, because here it was said that in the problem statement 20 degree centigrade is the temperature and 750 mmHg is the pressure at where the air is available to be supplied, right? So again here you can write directly N2, or then subsequently you can find out this much of N2 will occupy how much volume, right? So same thing here, N2 has been again assumed 1, right? At 293 means 20 degree centigrade temperature, 755 mmHg pressure, how much volume it will be occupying, right? So this calculation will give you 387.85 cubic feet of volume, right? Now how much N2 is there? 11.42. So to be multiplied. So you see here volume of air at 20 degree centigrade temperature and 755 mmHg pressure, which is the condition of air to be supplied, right, comes out as 4429.727 cubic feet, right. So this much of volume you have to measure, right, and send to the process, so that the stoichiometric requirement including the excess amount of air can be supplied, right. 20% excess exactly multiplied by the air requirement, right. So and there are many instruments which can measure the volumetric flow rate, so that much of air you can supply, right. Yes, so now volume of air per 100 cubic feet of ammonia, right. Ammonia volume, right, ammonia volume was 387.85 cubic feet, right, and air to be supplied, its volume comes out as 4429.27 cubic feet. So now volume of air per 100 cubic feet of ammonia comes out to be 1142 cubic feet, right. Just stoichiometric what you can say, elementary calculations, right. By elementary calculations you can find out the volume of air per 100 cubic feet of ammonia. So 11.42 cubic feet of air we have to supply, air available at the given condition, right. So such kind of calculations, such kind of very basic principles like ideal gas law we have to use, and we have to proceed with the calculation, right. So these calculations or similar calculations has been involved to understand the calculations sir has shown in the previous lectures, right. Yes, now the B part was, this is the answer of part A, right. The answer of part A, you can statement was calculate the volume of air to be used per 100 cubic feet of ammonia entering the process. So part A over. Now part B, calculate the percentage composition of volume of gases entering the catalyzer, right. So we will be making some diagram, right. So this is the diagram, okay. Air available and it is coming to the catalyzer, right. The ammonia 100 cubic feet coming to the catalyzer, right. Catalyzer is at 700 degree centigrade temperature, right, and the reaction occurs there is 4 lb mole of ammonia reacts with 5 mole of oxygen, and it gives us 6 H2O plus 4 NO, right. So this reaction happens here, okay, and then we send all the products and reacted, if it is okay, to the cooling tower, right. Yes, so we will see the cooling tower part in later stage, okay. Yes, so gases entering the catalyzer, okay. So how much ammonia we fed, how much air we fed, okay. So all we know, we have to summarize that, right. So here we know ammonia we entered 1 lb mole, right. Ammonia we entered 1 lb mole. Oxygen how much? 2.4 lb moles. Along with that nitrogen also came, right, because we supplied air. So along with 2.4 lb mole of oxygen, nitrogen also came. So how much nitrogen came? Total was 11 point something minus 2.4, right. Total air we had calculated, okay, that was air to be supplied 11.42 minus 2.4, that will be nitrogen, okay. So 9 point something, 9.02 lb mole. So in catalyzer these 3 components are coming, entering, right? 1 lb mole of ammonia, then 2.4 lb mole of oxygen, and nitrogen will be 9.02 lb mole, right? So we know the exact amount, right? We can find out their composition, right? For gaseous system, the mole composition is equals to volume composition, right? So 1 lb mole, 2.4 lb mole of oxygen, and 9.02 lb mole of nitrogen. Sum up, and then to each one you divide it by the total summation, multiplied by 100. It will give you the percentage, right? So you see here, 8% of ammonia, then 19.3% of oxygen, and 72.7% will be the nitrogen. Total will be 100%. So this will be the composition of gases entering to the catalyzer, right? So very simple. Okay, if any impurity comes, okay, you need to identify that, okay, and you need to quantify that. Accordingly, its percentage also you can calculate, right? For example, the air is containing some CO2, okay, and some other gases, okay. So if have been identified, we have eliminated all those things to remove the complexity, right, to make the problem more simpler, okay. Yeah. So now this was the composition of entering gases, okay. Now we have to find out the composition of leaving gases, right? So what reaction in catalyzer is taking place, that we have to look at. Accordingly, this 1 lb mole of ammonia is entirely converting into the products, or some unreacted remains. All those things we will be talking it out, okay, after the catalyzer, okay. And then its quantity we need to identify, we need to sum it, okay, all those, and again we will be calculating the composition, right? Yeah. So ammonia oxidized, okay, 85% is the conversion in oxidizer. That was given in the problem statement, okay. Otherwise you can again regain the question statement. Yeah. So 85% is conversion, then ammonia oxidized will be 0.85 lb mole, because 1 lb mole came, oxidized will be 0.85, okay. And in the exhaust, I mean in the outlet of oxidizer, right, there will be 0.15 lb mole of ammonia, right, 0.15 lb mole of ammonia will be there, right. So ammonia unoxidized will be 0.15 lb mole. Now oxygen we supplied, that is 2.4 lb mole, but how much is consumed and how much will be unused? So unused oxygen will go in the outlet, right? Unused oxygen will go. Yeah. So oxygen consumed will be, you see the reaction stoichiometrically. So 5/4 multiplied by 1 lb mole of ammonia if 100% conversion is, but conversion is 85%, so therefore you have to multiply it by 0.85. So oxygen consumed will be 5/4 multiplied by 0.85, which gives you 1.06 lb mole. So this much of oxygen only got consumed in the catalyzer, right? So 2.4 was supplied, 1.06 has got consumed, remaining will be there in the exhaust, in the outlet, right? So you see here O2 unused, 2.4 minus 1.06 is 1.34 lb mole, right? So oxygen unused is 1.34 lb mole. So you write down then, okay, at the outlet or exhaust of the catalyzer, what will be there? 0.15 lb mole of ammonia, right? Then 1.34 lb mole of unused oxygen, right? And nitrogen will be as it is, right? Along with air, there was nitrogen 9.02 something. How much it was? Yeah, so it will be as it is. Okay. Yes. Again, the reaction occurred and it gave us NO. Right? NO was formed. So how much NO has formed? So you refer the reaction and its stoichiometry. Right? So 1 lb mole of ammonia was giving 1 lb mole of NO. Here 0.85 lb mole of ammonia only got converted. So 0.85 lb mole of NO you will be giving. Right. So in the outlet again you have to chalk out that 0.85 lb mole of NO is there. Right. Then H2 also again that stoichiometrical you have to see 6 by 4 multiplied by 0.85. Okay, because ammonia will be the limiting reactant. Right, so everywhere we are taking care of that. Right, 6 by 4 multiplied by 0.85, that is 1.275 lb mole will be the water in the form of vapor. Right, so water vapor, then NO formed, O2 unused, right, and ammonia unoxidized. Right, and in addition to that the nitrogen as it is. Okay, so all those things we will be talking it out. Yeah, gases leaving the catalyzer: ammonia 0.15 lb mole, O2 1.34 lb mole, NO 0.85, H2O 1.275 lb mole, and nitrogen as it is 9.02 lb mole. Okay, so everything, okay, we have summarized. Okay, and then you can find out the composition. Molar composition will equals to volume composition for gases. Right? So composition of entering gas in previous part and composition of leaving gas in this part we have completed. Right? Yes. Now everywhere in the latter part, okay, they have asked the answers in terms of 100 cubic feet of ammonia if enters. So at that condition we know that any gas occupies 359 cubic feet of volume, right? So 3.26 lb mole of gas will occupy how much? So multiplied by simply 359, so 1170 cubic feet, right? So that was asked, volume of gases leaving the catalyzer at this condition. Yes, 1170 cubic feet was the volume at the special condition, that is standard condition. Now they have asked at this particular condition, so we can convert it. Right, here V1 we know that is 1170, the conditions already we know. Okay, at this condition 743 pressure and 973, 700 means 973 Kelvin temperature, right? So this V2, that is 4270 cubic feet of volume. Okay, so we have calculated that the volume of gases leaving the catalyzer at the given conditions will be 4270 cubic feet. Okay, so that will be our answer. So I believe that you are correlating the things. Okay, the physical things happening and how we are using our calculation steps and the basic understanding, right? So in this way we have to proceed with the calculations, right? And in last part what was asked, calculate the weight of nitric acid produced. Okay, how much nitric acid produced per 100 cubic feet of ammonia entering, means 0.258 lb mole of ammonia entering. Okay, because we have shifted the basic kind of things in between, right? Because molar composition or volumetric compositions, okay, so it is better to have basic in lb mole, right? So accordingly we have done. Then every calculations they were asked in terms of 100 cubic feet of ammonia entering, so accordingly we have shifted, calculated the exact lb mole of ammonia. Same that is 0.197 lb mole of HNO3 will be forming, right? So is it clear up to this point? Now the weight has been asked. Generally weight used to be either in lb or gram or kg or ton, right? So we have to use its molecular weight of HNO3, that is 63. So multiplied by 0.63, so 12.4 lb of HNO3 will be producing, right? So the problem statement why I selected, because it is something happening in the industry, right? And similar calculations we need to perform, okay, being an chemical engineer. Okay, how much air to be supplied, okay, how much volumetric flow rate, then okay, in 1 minute this much of volume will go, right? Or if per second, accordingly we can set the flow rate, okay, so that exactly or close to that amount of air will be supplied, right? So any questions? Have enjoyed the calculation? Huh? Okay, so thank you. I will ask our one of the valued participant, Dr. Kanti Kumar Athankar, who is Associate Professor of Chemical Engineering in the Department of Chemical Engineering at IPS Academy, Indore. Right. So he will be sharing his certain insights regarding the process calculations. So, Dr. Kanti Kumar, please.